In this video, we solved problems 1 and 2 from Differential Equations quiz number 5 from the spring 2021 semester. There were multiple versions of this quiz, or actually 3 versions of the quiz. So these are the problems 1 and 2 from version 2 of the quiz. Problems 1 and 2 cover standard G18, which is the method of undetermined coefficients. For the first problem, we're just asked to find the method of y, or the form of, of y sub p, and then the second problem we actually solve it. So let's read this problem statement and do it together. It says, use the method of undetermined coefficients to find the appropriate form of y sub p. Do not solve the differential equation and do not find y sub c. So most of the time we would have to solve the corresponding homogeneous equation first, and then we would have y sub c, that's the complementary function or the complementary solution. It's the solution to the corresponding homogeneous problem. And then we would make an educated guess based on the right-hand side. And then we would modify that guess based on the form of y sub c. That's what we would typically do. But this time we're not asked to do that. We're not asked to find y sub c. All we're asked to do is look at the right-hand side and find the appropriate initial guess for y sub p. So we're going to let y sub p equal whatever is appropriate given this right-hand side. So when I look at this, I see a second degree polynomial times sine of x. Now, derivatives of sine of x and cosine of x lead to sine of x. So when I'm coming up with my educated guess here, I'm going to guess a second degree polynomial. So ax squared plus bx plus c times sine of x, but also a second degree polynomial, picking up where I left off, dx squared plus ex plus f times cosine of x. If you have a sine of kx or a cosine of kx on your right-hand side, you're going to have a sine or you're going to have both the sine and cosine of kx in your guess for y sub p, because derivatives of sine and cosine lead to sine of x. Okay, here I have a constant times e to the negative 8x. So I'm going to guess that we have a term that is a constant times e to the negative 8x in our y sub p. So I'm here, D, E, F, G is my next letter, times e to the negative 8x. And then this right here is a fourth degree polynomial. You don't want to think of this as separate from this. You want to think of it as a polynomial, fourth degree. So we'll just come up with one fourth degree polynomial here. So we have g, then we'd have h times x to the fourth, I times x cubed, j times x squared, k times x, and l. So h-i-j-k-l, yes. So that is our educated guess. Now there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 constants there. If we were actually solving this differential equation, we would first have to find y sub c. We would come up with this guess. We would multiply by extra x's as appropriate, depending on whether we have any terms on this list that are terms in y sub c. And then we would differentiate 3 times, substitute into the differential equation, and set the left-hand side equal to the right-hand side. And then we would set the corresponding coefficients of functions on the left-hand side equal to the coefficients of the corresponding function on the right-hand side. And that's because of linear independence that we can do that, the linear independence of all of these functions. But that would lead to eventually a system of 14 equations and 14 unknowns. So I would not have you do this by hand. I mean, if I wanted you to solve something like this, we could use Mathematica or some technology in order to solve that system of 14 equations and 14 unknowns. But on this problem, I was just making sure that you understand how to get the guess. So it's second degree polynomial times sine plus second degree polynomial times cosine, constant times e to the negative 8x, and then an appropriate fourth degree polynomial there. Okay, in problem 2, we're asked to actually find a solution, and maybe I should be more specific. Let's find a general solution to the non-homogeneous differential equation using the method of undetermined coefficients. In order to do that, we always start in the same way. We need to find our y sub c so that we can make an appropriate educated guess for y sub p. In order to find our y sub c, we need to solve the corresponding homogeneous problem. So we set the left-hand side of the differential equation, which includes all of our derivatives and y's, we take that and we set it equal to 0, and we solve this problem instead. Now, since this is a constant coefficient differential equation, we're going to let y equal e to the mx. Since it's fourth order, we're going to compute the first derivative, second derivative, third derivative, and fourth derivative. And once we find those derivatives, we're going to substitute those into this equation. That's going to give us an equation involving m. If we can find the values of m that satisfy that equation when we substitute, those will be the values of m that cause e to the mx to be a solution to this equation. So that's the plan. The derivative of e to the mx is e to the mx times the derivative of the inside by the chain rule. The derivative of a constant times x is just your constant. Bring your constant down, multiply by the derivative of e to the mx again. You get e to the mx times the derivative of the inside, which is another m. So I have an m squared there. So every time we take the derivative, we get another m. An extra m factor, that's due to the chain rule. And then we take these guys and we substitute into the differential equation, and we'll end up with this algebraic equation involving m. So our fourth derivative of y goes here, and we're subtracting 2 times this third derivative of y, and then we're adding the second derivative of y, which has an m squared e to the mx in it. We're setting that result equal to 0. You want to factor out the exponential. E to the mx times m to the fourth gives us our first term. E to the mx times a negative 2m cubed gives us our second. And this times a positive m squared gives us our third. This times this equals 0 if one of the factors is 0, but the exponential is never 0. So we have that. And you can factor out an m squared. So have a greatest common factor, so we should always take that out. And then this m squared minus 2m plus 1 factors pretty easily. I need 2 numbers that multiply to give me 1. Well, 1 and 1 will work. That add to negative 2. If they're both negative, negative 1 plus negative 1 is negative 2. So we have this, which means we have a repeated root, m squared there, and then we have another repeated root. It's m minus 1 squared. So that is our factored characteristic equation. Or you can think of that as factoring the characteristic polynomial on the left-hand side. Okay, so if this times this equals 0, that means either the first factor equals 0 or the second factor equals 0. Since that is squared, we have 2 roots associated with this. So m1 and m2 are both equal to 0. Here, if I take the square root of both sides and add 1 to both sides, I get m equals 1, but it's squared. So there are 2 roots that are equal to 1. So we've got repeated roots. Remember how repeated roots work. y1 is going to equal e to the m1x, so it's e to the 0. E to the 0 is 1. And y2 looks just like that, but you multiply by an extra x. So it's going to be e to the 0 times x, or x. y3 and y4 are over here. If m is equal to 1, this is going to be e to the m3x, or e to the x. And then because it's a repeated root, you're going to multiply by an x to get the second linearly independent solution. So we've got 2 solutions, 1 and an x for the root of 0. And then we have those 2 solutions of e to the x and x e to the x for the second one. So you can put those together to write down the general solution of the corresponding homogeneous problem, which is y sub c. So we have c1y1 plus c2y2 plus c3y3 plus c4y4 which in this case is C1 plus C2x plus C3 e to the x plus C4 x e to the x. Okay, you got to keep that in mind when we look at the right-hand side and come up with our educated guess. So now we're going to focus on solving the non-homogeneous problem. And we'll come up with our initial educated guess of a constant for the 1, and then we have a constant times e to the x for the e to the x. But we always have to compare these terms to the terms in the solution over here. Now, a constant is a solution to the homogeneous problem. So that constant a, if I substitute into the differential equation, I'm not going to get 1. If I take the derivative of that 4 times and I plug it in over here, I'm going to get 0, not a 1. So we multiply by x and we say, okay, is that on the list for our y sub c? Well, a constant times x actually solves the homogeneous problem as well. So if I take constant times x and I differentiate 4 times and substitute over here, I'm going to get 0, not a 1. So I multiply by an x again. Do I have a constant times x squared on that list? I don't, so I'm good. Notice we have a constant times e to the x here and a constant times x times e to the x there. So I can't use a constant times e to the x here. I need to multiply by x, and that's already on the list, so we multiply by x again. That one's finally not. So our y sub p is this. I think I'm going to write it a little bit neater. I'll write it this way. And that is our y sub p. Alrighty. Now we want to differentiate 4 times and substitute into this equation because we're assuming that y sub p is a solution to this differential equation for some unknown constants a and b. We just have to find a and b so that this works. To find a and b, we differentiate 4 times, substitute, and we set the left-hand side equal to the right-hand side. So we will first compute y sub p prime. This is just the power rule. Bring your constant down. Derivative of x squared is 2 times x to the 1 less power, which is 2 times x to the first. Over here, I've got a product. Here's my first function, and there's my second function. According to the product rule, we'll have the derivative of the first times the second, plus the derivative of the second. Derivative of e to the x is e to the x, times the first. And with these guys, I would factor out the e to the x. That way you don't have to use the product rule twice when you differentiate again. Got to go up to the 4th derivative, so we got to keep going. All right, take the derivative again. This is the derivative of a constant times x. The derivative of a constant times x is just the constant. Here I need to use the product rule. There's my first function. There's my second function. According to the product rule, we have the derivative of the first. Derivative of a constant times x is just the constant. Then you bring your constant down. Derivative of x squared is 2 times x to the 1 less power. It's derivative of the first times the second, plus derivative of the second, which is e to the x, times the first, undifferentiated. And then you're looking at this, and you see that they have the e to the x in common. So I want to collect like terms. I think I'm going to write it with the lowest power of x first. So we'll have the constant here. And then I've got my x terms. I've got 2bx plus another 2bx. So that's 4b times x. And then the last one is bx squared. And it's multiplying e to the x. Okay, so that's y sub p prime and y sub p double prime. Let's compute y sub p triple prime. The derivative of this constant is 0. We've got a first function and a second function. According to the product rule, we have the derivative of the first times the second plus the derivative of the second times the first. And we'll collect like terms again. You have your bx squared first. And then I'll have my, I need to be consistent. That's okay. We'll be consistent whenever we add at the end. I've got my bx squared. If I want to add my x terms now, I've got 2bx and 4bx, so that's 6bx. And then I've got 2b and 4b, which is 6b, all multiplying e to the x. We've got fourth order differential equation, so we've got to compute one more derivative. There's our first function, and there's our second function. Using the product rule again, we have the derivative of the first times the second, undifferentiated, plus the derivative of the second times the first. Okay, collect like terms. Got my x squared term right there. My x terms, I've got 2bx and 6bx, so that's going to be 8bx. Oops, I don't want to do that yet. And 6b plus 6b is 12b. And all of that's multiplying our exponential. Okay, so we're assuming that y sub p is a solution of this fourth order differential equation. So we're going to add these terms on the left-hand side and set them equal to a right-hand side. Now we can see just from doing this that our y sub p, the fourth derivative is kind of long, and so is the third derivative, and so is the second derivative, and we have to substitute all of those over here. So rather than just writing them all in one line, which is a little bit difficult to just sort of look through to keep track of terms, we're going to add vertically. So just like in elementary school, if you had 5 minus 3, often on a flashcard, you'd see something that looked like that, 5 minus 3 equals 2. We're going to do something like that here, but with the derivatives of y. So we're going to substitute into the differential equation, but we're going to stack the terms vertically. To make our lives easier, and then we'll collect like terms in columns. Okay, so the fourth derivative of y is right here. So you've got bx squared plus 8b times x plus 12b times e to the x. And then I want to take y triple prime and I want to multiply by -2. So I'm taking this guy and I'm multiplying by -2. So each of these terms will get multiplied by -2. So I'm adding -2bx squared minus 12b times x. And -2 times that is minus 12b. And then I want y sub p double prime, which is right here. So we're adding that 2a, which is its own thing, so it goes in its own column. And then I've got this guy, I put it in a different order, but so I'm going to change the order a little bit now. Well, my x squared term is bx squared, my x term is 4bx, and my constant term is 2b. I'm going to add like terms in columns. I've got bx squared and bx squared, that's 2bx squared, minus 2 of those are gone. I've got 8 and 4 of those, that's 12, minus 12 of those, so those are gone. And the 12b and the -12b are gone. So we just have the 2b times e to the x plus 2a. And we're going to set that equal to the right-hand side of the differential equation, which was 1, that was my constant term, plus an implied 1 times e to the x. Now, 1 and e to the x are linearly independent functions. So that means that the only way this left-hand side can equal this right-hand side is if the coefficient of e to the x on one side is equal to the coefficient of e to the x on the other. And if the constant term on one side is equal to the constant term on the other. So we have two equations and two unknowns, 2b equals 1 and 2a equals 1. And it's easy enough to solve for a and b. Turns out a and b are both 1/2. So we substitute it into the differential equation, set the left-hand side equal to the right-hand side, set the corresponding coefficients equal to each other because of linear independence, and then you've got two equations and two unknowns. You want to solve those for A and B. And then once you have your A and B, you substitute those into your y sub p. These are the values of A and B that are necessary for this to be a solution to this problem. That's what we just found. So A is 1/2 and B is 1/2. We'll substitute those into our y sub p now. So y sub p is 1/2 x squared plus b, which is 1/2 times x squared times e to the x. And if you want, you could factor out a 1/2 x squared. That'd be fine. You don't have to, though. Okay, now we want the general solution. We know the general solution is y equals y sub c plus y sub p. We always like to have an interval I as well. So our general solution is y equals that sum, which in this case happens to be y sub c, which was right here. C1 plus C2x plus C3 e to the x plus C4 x e to the x. Plus y sub p, which is this. And this will work for all real numbers. And that's it.